Hello, my name is Nicholas Rosano, and this is my computer science problem presentation. And my problem is the maximum subarray. The maximum subarray is a list of, you take an array, and the thing about this array is it can consist of negative and positive numbers. And the idea is you want to find, you need to split it into subarrays, but you cannot change the order of the numbers. So if it's 1, 2, 3, 4, you can't switch 4 and 1 or 3 and 1. You just can't. They have to be in that order, like 1, 2, 3, 4. And what you're looking for is when you find these subarrays is you're looking for the largest one, like the sum that is the largest of all the other sums you could possibly find. And these subarrays can be anything from one element to the entire array, if need be. Usually it won't be, but it's always possible. Anyway, like I said before, this can be just one element too. So if it's, let's say it's a 1 out of a list of entirely negative numbers with the exception of 1, it would just be 1. So this is my pseudocode. As you can see, you have, your max subarray. You'd have your own array to put in here, and you'd have this, you have your functions, blah blah blah, like in A. You typically split them in half, which is why I have a left subarray and then right subarray. I've implemented them. You look for the minimum, and this is like a function. It's supposed to be like the minimum, like the smallest possible integer. I don't know. And then we have, my two loops, loop 1 and loop 2. And then you have, your solution, which is the maximum of the left and the right. And I don't know, it's kind of difficult, but it's a little more difficult to get the single element thing using just the pseudocode, but and you have, you return your max. You have the solution plus this. Right, so the brute force way is the simpler way, the simpler way to solve it, but it's not an efficient way, as you'll see. It's all the possible outcomes, and without really doing much, you can already tell, since there's two loops, and there's really no way to do this without two loops, it's going to be O n squared, the big O of n squared, which is not too efficient. Because you have to do every possible answer, and in order to do that you have to go through both, and so that's that. Next one is divide and conquer. In this case I'm going to give I have an actual example in this slide. I have this array, and so what you do is you take those of these, you put them in half, and so you try to find the best possible sum, which is either either it's like one element or several elements, and as you can see, the best out of both of these is 7 and 10, and you have those. And then you bring it back together just to see if there's even one that's even larger. And in this case there isn't, it's just 10. And if you wanted the written, the thing for it, the master theorem, it would just be t of n equals 2t, because there's two functions, and then there's n over 2, and then just n. And if you simplify that, which I'm not going to write out the entire thing, you use case 2, by the way, because in this case, if you do the math, the log b of a is the same as c, which is, they're both 1. So they're equal to each other, so that's case 2, and if you simplify it, you get O n log n, which is significantly better than O of n squared. This brings us to the final thing, the asymptotic complexity. So as we went over brute force, the runtime is O n squared, which is quadratic. It's not very efficient. And with the divide and conquer, it can be reduced to n log n, O of n log n, which is better, but it's not great. However, there is another method which I'm not going to mention because we haven't covered it yet. And this is just supposed to be divide and conquer, but just in case someone wanted to know, it can be reduced even further down to linear time, or O of n. Alright, well, that's my presentation. Okay.